Memristors are devices that change their resistance between two or more states when electrical stimuli are applied. The switching effect is related to a movement of a few atoms within the device, and it requires very low amount of energy and space. These genuine properties are very attractive for the fabrication of non-volatile memories and artificial neural networks. Neuromorphic engineering can produce advanced circuits to accelerate artificial intelligence software. For this application, resistive switching devices are promising alternatives to mimic biological synapses due to their operation similarities and versatility. We have fabricated advanced memristors using a novel two-dimensional material called multilayer hexagonal boron nitride. We started by depositing the bottom electrodes on a silicon wafer with a layer 300 nanometer thick of silicon dioxide on top. Each electrode consisted of a squared pad with an area of 100 micrometer by 100 micrometer connected to a metallic wire with 5 microns width. The electrodes were deposited by photolithography, electron beam evaporation, and liftoff. Each electrode was formed by evaporating 10 nanometers of titanium and 40 nanometers of gold. After that, we used a sheet of commercially available hexagonal boron nitride and transferred it on the bottom electrodes. Finally, top electrodes, similar to the bottom ones but rotated 90 degrees, were deposited to form Memristor devices. The hexagonal boron nitride synthesized using this method contains some native defects, and we consider them in our simulation study. It is known that regions of high density of defects favor Memristor resistive switching operation. Conductive nanofilament formation is linked to defect-rich regions where a high concentration of boron vacancies is found and where metallic ions can diffuse. In our simulator, we represent the dielectric conduction properties with a three-dimensional network of resistances connected to the metal electrodes. Since our dielectric is 6 nanometers thick and approximately consists of 18 layers of hexagonal boron nitride, for symmetry reasons we consider a cube with 18 layers of resistances in each direction. The devices were characterized by using a Keysight B1500A semiconductor parameter analyzer connected to a probe station. A B1511B medium power source measurement unit module was employed for quasi-static ramped voltage stress. See the current versus voltage curves obtained under ramped voltage stress. The resistances of the simulator network can be switched between 4 different values, as if they were complex circuit breakers. Different resistance values are used for the circuit breakers in the planes, corresponding to the boron nitride layers, and the vertical circuit breakers to reproduce the features of two-dimensional materials. A device with a pristine dielectric is assumed to start the simulation. We can either choose some resistances to be in the low state randomly or include areas of defects with a high probability of low value resistances. This is a more realistic approach, as these regions are usually found in the dielectric. Depending on the voltage difference on each resistance, the initial high value is switched to a lower value in the forming and set processes. In this manner, the conductive nanofilaments are formed. Charge conduction is filamentary, and once the filament is formed, a reset process begins. A long series of cycles formed by successive set and reset processes can be simulated. For the switching of the circuit breakers, a similar approach can be followed using the temperature calculated on each resistance in the network. A threshold temperature is defined to switch the resistor. The simulator reproduces correctly both the experimental reset and set curves. In addition, both experimental and simulated current curves with decreasing steps can be seen. These steps are linked to the rupture of a conductive branch, which is part of a complete conductive filament. In other words, this phenomenon is a partial filament destruction.